Okay, we're going to learn a new method for solving pairs of equations. And sometimes kids I know like to say, well, once you know how to do it, why learn another method? Well, this method is sometimes easier. Okay? Now, the previous method we learned, the substitution method, has a big advantage, which is why we taught that first. Namely, it'll always work. This method will also always work with linear equations, but it will not necessarily work with other kinds of equations, if there's, say, x squareds or other kinds of things involved. The substitution method will always work. So that's the one to have as your backup. Now, this method, when you can use it, will often provide easier solutions. So it's a matter of taste. Whichever way you like to solve it, fine, but make sure that whatever methods you know, make sure that one method is the substitution method, because that's the one that you have to fall back on when nothing else will work. All right, let's look at this. Notice that this pair of equations has an interesting little thing here, which is that this has a plus 3y term, and this has a minus 3y term. What's going to happen if we simply add the two equations together? Okay, notice if I just simply add the two equations, 5x plus 7x is 12x, 3y minus 3y goes to 0, and over here 25 minus 1 is 24, and then I get 12x is 24, divide both sides by 12, and I'd get x is equal to 24 over 12, which is simply equal to 2. Okay, that was pretty straightforward. Now, that gives us x. All right, how do you find y? Well, we can go back to our substitution method and find y. So I like to first of all solve for y and then plug it in. I could plug in the 2 and then solve for y. So let's rearrange this first equation. You could take either equation really. So I'll have 3y is equal to 25 minus 5x, and let's go ahead and divide by 3. So now let's plug in the 2 here. So if x is 2, y is 25 minus 5 times 2 is 10 over 3, which is 15 over 3, which is 5. So the solution would be the ordered pair 2, 5. Okay, so xy, the solution would be that. Okay? Now, you have to admit this was a pretty special circumstance to have a 3y and a minus 3y. Okay? Let's try another one. Well, here it looks almost as interesting, but except this case they have equal ones, equal terms, 4x and 4x. And so now, if I wanted to add them, they wouldn't cancel out. I could subtract them, but it's actually better if you do that in 2 steps. If I take one of the equations and multiply through by minus 1, it'll change one of the 4x terms into a minus 4x. So let's multiply every term here by minus 1. So just think of these as minuses in front of the terms. And now, if you add, you get 0 for this term. 9y minus 3y is 6y. And here you have 75 minus 33, so this is a 2, this is a 4. So 6y is 42. Y is equal to 42 over 6, which is equal to 7. Okay. Now plug in 7 for y in either one of these equations. Let's take the second one. We messed up the second one. Let's use the first one. So if I want to solve now for x, we would have 4x is equal to 75 minus 9y. And then if I divide by 4, I would have this. So let's plug in our 7 here. Okay, so 75 minus 9 times 7. 9 times 7 is 63. So x is 75 minus 63 over 4. 75 minus 63, so that's 12. So x is equal to 12 over 4, which is 3. Okay, so now I remember to put my x first in the ordered pair, so I have 3, 7 is my xy. Okay, so what we've seen is that if we don't have that special circumstance of equal terms except opposite sign, equal absolute values, opposite sign really, then we can sometimes force it into that circumstance. In fact, we can pretty much always force it into that circumstance, as we'll see next. So, for instance, pick a term. Shall we eliminate the x's or the y's? Let's eliminate the x's. Okay. I just chose that. We could do it literally either way. Notice that if I multiply this first equation through by 11 and multiply the second equation through by 2, that this is going to become a 22, and so is this. Okay, well, let's see what happens. So, if I move them over here, 11 times each of these terms is 11 times 2 is 22x. 11 times 3 is 33, so it's minus 33y. And 11 times 8 is 88, minus 88. And the second equation, I have 22x plus 10y. And 2 times minus 1 is minus 2. Okay, one last step. Notice we have equal terms, but just like in the last case, we need to change the signs on one of them. So let's change the signs here. So multiply through by minus 1, and that becomes a plus. Okay? Now when we add, these go away. 33, minus 33 and minus 10 is minus 43. And minus 88 plus 2, you take little from big and the sign of the big, so 2 from 88 is 86. It would be minus 86. Okay, multiply by minus 1 and divide by 43. So y is equal to 86 over 43. And what do you know? It's just double, so this is equal to 2. Okay, so once I know that y is equal to 2, I can substitute back in here, for instance. And so I have 2x is equal to minus 8 plus 3y, and then divide by 2. So x is equal to this. Let's put the 2 in for y. And so x is equal to minus 8 plus 6 over 2. Well, little from big and sign of the big is minus 2. So this is minus 2 over 2 is minus 1. So the solution, xy, is going to be equal to minus 1, 2. Okay. So there you have it. If I find some pair of numbers so that I can multiply through by this pair of numbers to change these into equal coefficients with opposite sign, and I usually just do the opposite sign as a separate step. I find that a lot of times working with negative numbers being a little bit less familiar than positives, it's easier to make mistakes, so just handle it separately. Okay? And what numbers can we use? Well, 2 and 11 are pretty clear. If I multiply this by 11 and multiply this by 2, these will come out the same. If I wanted to equate these, notice it has the advantage that I wouldn't have to change the signs because they're already opposite signs. I could have multiplied the top equation by 5 and the bottom equation by 3. That would have given us the same result. Okay. What if I have a pair of numbers like, say, 4x plus something or other, and down here I have 6x minus something or other, or whatever, okay? And I want to make the x terms equal. I don't really need to multiply the top by 4 and the bottom by 6 because they already have some factors in common. And so you can really treat this like a least common denominator kind of problem and say, what factors do I need to multiply this by so that it'll have all the same factors as down here? I want to make them both equal to something with equal factors. So this one has a 2 and a 3, and this one has a 2 and a 2. So you say, what does this one have that this one lacks? Well, how about a 3? What does this one have that this one lacks? Well, another 2. And now if I try that, what is 3 times 4? 12. This would be 12x. What is 2 times 6x is 12x again. So this type of a technique, treating them like adding fractions and finding the common denominator, is a method that will work. Okay, so is this easier? Well, the first step is frequently easier. The second step is very much like doing substitution, isn't it? So the second half of the problem is pretty much doing substitution anyway. So you can have your choice. It is important to learn this method because there are other methods down the line, especially when you go to, say if you have a problem with 5 equations and 5 unknowns. It turns out that if you have the same number of equations as unknowns, you'll be able to solve the same way. We're not going to do that this year, but some of these techniques for solving bigger problems like that are built on this technique. So it really is important to learn this technique, which is called elimination method. Use this as well as the substitution method and get so that you're comfortable with both. Okay.